In this video, we're going to go into some detail about the physics of how a quadrupole works. Now, don't worry, I'm not going to beat you up on this on a quiz, but many of you will find that once you've been through this exercise, I'm going to keep it pretty simple, keep the formulas to a minimum. You'll have a much better understanding of how a quadrupole works, and that'll help you design better experiments. So that's our goal here, is to design better experiments. So where do we start? Right here, we're looking at a cross-section of the quadrupole. There's 1, 2, 3, 4 quadrupoles, okay? Well, there are 4 poles. Now, really why it's called a quadrupole is that between these, there's a dipole and there's a dipole here, and so it's a field with 2 dipoles, okay? The quadrupolar field. Okay, now to explain and describe fields like this, or to model them, we could just look at Coulomb's law. Very simple. Force equals some constant times charge 1 times charge 2 divided by r squared. Some of you, not all of you, your eyes will gloss over when you see this and you're going to be scared. And so, well, let's talk about it. I've written it here. You can pause and actually just read this, or we'll get to it on the next slide. Now, what does this mean? And what should it mean to you? Well, what it could mean to you is the following. Force equals K times the charge on the rods, whichever rod you're closest to really, the charge on the molecule divided by r squared, where it could be all the rods, but the point is when you're close to one rod, you're going to feel it a lot more because of this r squared relationship. Is it still too scary? Well, think of it this way. Force equals some constant divided by the distance between the 2 charges squared. Now, if that still doesn't make sense, that's okay. Let's escape out of here, go to the web. I love this website for, you can see everything I'm up to on my computer, nothing but business, huh? So I'd like to go, just type Wolfram Alpha. All right, that'll bring you to this. And you can graph just about any equation, and so that's great. Let's just go 1 over r, and it's already there for us, squared. And we're going to look at a graph of what that means mathematically. I'm going to zoom in on it. Just control plussing. All right, so this is our 1 over r squared graph. So at some distance, here's your ion. It's not feeling very much at all, and then it gets closer and closer to the it's an ion. It's getting closer and closer to the pole itself, to the metal quadrupole, and now it's feeling an enormous force. And look at the force go up really fast with distance. That's a 1 over r squared relationship. Now, that shape, since there's a pole here and there's another pole over here, that shape makes a saddle. Right? You have the same exact function on the other side. Of course, you have another pole here and another pole here, and we'll get to those in a second. So let's escape out of here. Let's go back to PowerPoint. All right, so now you know what an r squared graph looks like, 1 over r squared, and that's where this saddle potential, well, and that's why I show you this macroscopic rotating saddle potential. It means that if you're this positively charged ion, and this is a negatively charged pole, you want to roll down it to get to the negatively charged pole. Conversely, if you're a positively charged ion stuck in this potential, it's going up like this, there must be a positively charged pole here. So you feel a completely different, you want to roll toward the negative, you want to roll out and away from the positive. And so what does this do in a simple sense? So here's how our normal experiment will go. Field is, you feel in the field, you're positive ion. Oh, feeling in the field, you got to bounce back over there. But you get there and you, oh my gosh, you're feeling that field too. Now this is the simplistic view. And you're an ion in this potential. Really, you're going to do this, like kind of roll down it. Okay? So again, the ion is there in this potential well, and this is how the well would relate to the picture we've shown here. And it just wants, back and forth between these 2 positives, and it wants to get to the negative. And if you let it, it'll get to the negative, it'll hit the pole, and it'll be gone forever. So, watch this pole, and watch what we're going to do here. We're going to, before this ion can get over to the negative, because it's going to stick to the pole, we switch the polarity. Now it's like, ah! And now we know that the field lines are a bit not completely straight. They're kind of this saddle potential. Excuse me. This shouldn't have done that. Okay. So back to here. Here's the ion. It has this crazy shaped field. Now we know it's just not bouncing back and forth. It's actually kind of doing all kinds of neat things. It's like, whoa, I'm going this way and I'm going that way, but I get over here and oh, I feel the field, and I feel it really heavily once I'm close to the poles. All right, this is your qualitative field or feel for this. Okay. Now look at, you're seeing your saddle potential, and it's reoriented because the polarity is reoriented. We have switched the polarity. That means the charge of our individual rods. Now, that's just a cross section, but this is going through time. And so remember, this thing is moving in and out of the screen at a certain direction. And so you're looking at the XY direction, that's the field of the screen, but in the Z direction, it's actually doing all this crazy stuff. Whoa, it's going X, Y, Z, and it's moving, back further with time, okay? And so that's why you're going to see graphs like this when you see a simulation of a 3D ion trajectory. It's pretty funky. There's your X, and that's your Y, so that's where there's a pole here, there's a pole here, there's a pole down here, there's a pole over here. And this Z is going through the instrument. And right, it's a funky little trajectory that the ion has to go through when you simulate it. Thanks to my old colleagues Michael Henchman and Colin Steele, who actually built a quadrupole just for teaching at Brandeis. It was pretty cool. Now, I'm going to give you just a quick overview of how the quadrupole works in real time. Well, not real time. This is time. The whole time here is about 1/1,000,000th of a second. That's why you would use a megahertz frequency. That means 1,000,000 hertz, 1,000,000 times per second. Now, pay attention. These are our quadrupoles. Quadrupole 1, 2, 3, 4. And with time, so here we are, red, red. See, now if we're an ion and we're right here and we're positive, we're moving toward this red pole. But now it starts. It changes. Now it changes back. Oh my God. I'm an ion and I'm just going crazy. Okay. So you have this ion moving here that can't quite get home. Again, let's look at this again. Time. As time moves, the polarity is switching. So our positive ion keeps going in circles, basically, never able to hit a pole. Now, ions and electrons have been trapped, last I know, the record was 10 months. You could do this forever. That is how transmission works. In other words, if you just want to move all ions through a quadrupole, that's all you have to do. Apply a radio frequency and give them a little bit of speed and they'll just go through. If you want to separate ions, you have to do one more thing. Remember, this guy, and this guy, and this gal, and this gal are connected to each other by a wire. They can make a circuit. So all you have to do is offset the voltage here and the voltage here. And if you put an offset in that voltage, and this is all described here, you can pause this if you want to read it in detail, then you have something different. Okay? And now you can imagine if you're an ion, okay, these guys have more voltage and you're drawn more to them. Even though the polarity switches, there's always going to be more pull this way. And so that's going to draw the ions to a certain set of poles with a greater frequency. And then they're going to hit them more often. And so that's where those crazy stability diagrams come in from your book. There is a DC voltage, say that's 1,000 volts that you offset two poles. And the RF voltage, when we were going back and forth, there had to be a voltage when we were going from, negative to positive, and that's, let's say, 3,000 volts. So with DC voltage and RF voltage, there's a place for every particular ion of stability. All right? So this is called the scan line. So you actually have, at this particular RF voltage, whatever it is, and this DC voltage, Only thing that's getting through your quadrupole is M over Z19. Okay? Now, if you want to get M over Z21 through there, you got to increase the DC voltage and increase the RF voltage. And so that's the scan function of a quadrupole. I hope that demystifies it a little bit for you. A lot of that can get lost in the book, and what you really need is a qualitative sense of what's going on in this instrument so that you're not intimidated and that you feel empowered to develop all of your own experiments.